For millennia, we have told ourselves a story of solitude, a story of a single brilliant spark of life, our life kindled on a lonely rock, orbiting a solitary star. We drew maps of our celestial home, our solar system, with a firm and final border and edge to our known reality. Beyond it lay only an abyss, a wilderness of unimaginable scale, a silent, eternal and isolating darkness between the stars. We believed ourselves to be an island universe, a cosmic refuge, self-contained and profoundly alone in the grand silent ocean. The space between suns was thought to be a perfect void, a sterile chasm so vast that nothing could ever hope to cross it. The distances are simply too profound, the timescales too immense. 1 trillion kilometers is a meaningless number to the human mind, yet it is but a single step on the path to the nearest star. For a traveller to complete such a journey is a statistical fantasy, a voyage that would require an eternity weathering the cold, the radiation, the sheer crushing emptiness of the interstellar medium. Anything born around another star was destined to die there, forever bound by the gravitational leash of its parent sun. That was the story we told ourselves, the truth we accepted. A truth that made us feel unique, perhaps precious, but also trapped. Our cosmic neighbourhood with its 8 planets and countless asteroids was a closed system, a family album with no pages for strangers. Every rock, every comet, every fleck of dust we had ever studied was a native of this place, born from the same primordial cloud of gas that collapsed to form our sun some 4.5 billion years ago. They were our siblings, our cousins, all part of the same ancient lineage. We studied them to understand our own origins, to read our own past. And in all that time we had never ever received a visitor, not a single verifiable object that we could point to and say, with absolute certainty, that is not from around here. The great cosmic ocean had never sent a single piece of driftwood to wash upon our shores, until it did. The story of our solitude was about to be proven beautifully and terrifyingly wrong. It began not in a state-of-the-art mission control room, nor with the monumental gaze of a billion-dollar space telescope. It began with a man a telescope he built with his own hands, and a stubborn, passionate patience that bordered on obsession. On a quiet night in August 2019 from his observatory in Crimea, amateur astronomer Gennady Borisov was doing what he always did, scanning the celestial tapestry, hunting for the faint ghostly smudges that betray the presence of a new comet. He was a master of this craft, a modern-day celestial cartographer, charting the ephemeral wanderers of our own solar system. He knew their patterns, their behaviours, their predictable paths, as well as an ancient mariner knew the currents and the tides. Comets for him were familiar creatures if elusive ones. They swing in from the frozen frontiers of our system, from the Oort Cloud on vast elliptical highways, loop once around the sun, and then begin their long, slow journey back into the darkness. Their orbits are a family signature, the mark of their belonging. But on this night something was profoundly different. A faint point of light appeared where no known object should be. It was moving with a purpose, a velocity that felt unnatural. Borisov tracked it, logged its position, and with a growing sense of unease shared his findings with the global astronomical community. This is how discovery often works in our time, not as a singular eureka, but as a cascade of information, a ripple of curiosity spreading from observatory to observatory, from screen to screen across the planet. In Arizona, in Hawaii, in Chile, powerful telescopes swiveled to catch a glimpse of this new apparition, this celestial ghost. And as the data poured in, the unease in the community began to curdle into a sense of profound electric shock. Computers at the Minor Planet Center began to trace its path, not just where it was, but where it had come from. They tried to fit it to an ellipse, the classic closed-loop orbit of every comet, planet and asteroid native to our solar system. The models refused. The math simply broke. The object's trajectory made no sense. It wouldn't loop. It wouldn't return. It was not falling towards the sun so much as it was grazing past it, a bullet fired from an unseen rifle in the depths of space. The path it was carving through our home was not an ellipse, that familiar gentle shape of capture and return. It was a hyperbola, a perfect sweeping open-ended arc. This single geometric truth carried a revelation so staggering it would fundamentally alter our perception of the galaxy. A hyperbolic orbit is a one-way ticket. It is the signature of an object moving so fast that the sun's gravity, the most powerful force in our entire cosmic neighbourhood, could not hope to capture it. It could bend its path, yes. It could tug on it, alter its course, but it could not make it stay. This wanderer was not from here. It had not been born in our nebula. It had not spent billions of years circling our star in the distant cold. It had come from the void. It had journeyed from the gravitational well of another star. This was not a sibling. This was not a cousin. This was an alien. The first of its kind we had ever clearly seen. A true, unambiguous interstellar visitor. The official designation came swiftly, 2I Borisov. The I stands for interstellar. It was only the second time in history that prefix had ever been used. The first for the bizarre cigar-shaped object known as Oumuamua had left us with more questions than answers. Oumuamua was a fleeting enigma, a dark, tumbling rock that gave away almost none of its secrets before it vanished. It was a sealed letter we never got the chance to open. But Borisov was different. As it drew closer to the sun, it began to behave like a proper comet. The sun's heat, a celestial blowtorch applied to its ancient frozen surface, caused it to sublimate, to shed its very essence into space. It grew a coma, a phantasmal atmosphere of gas and dust, and then a faint but unmistakable tail. This was the single most electrifying development imaginable. Oumuamua had been inert silent, but Borisov was speaking. It was actively releasing the material from which it was forged, vaporizing the very stuff of its homeworld into a cloud that we from tens of millions of kilometers away could analyze. For the first time in human history, we did not have to guess what another solar system was made of. We had a sample, a tiny, pristine, cryogenically preserved piece of another star's nursery delivered directly to our front door. A wave of urgency swept through the world's observatories. This was not a mission with launch windows and project plans. This was a cosmic accident, a fleeting opportunity that would last only a few months before Borisov's incredible speed carried it back out into the unending night, lost to us forever. It was a race against the immutable laws of physics. Every great telescope on Earth and in orbit above it was commandeered, their schedules wiped, their missions reprioritized. The Hubble Space Telescope, the Very Large Telescope in Chile, the Keck Observatory in Hawaii, humanity's greatest eyes all turned their gaze from distant galaxies and familiar planets to focus with desperate intensity on this single ghostly point of light. They became our chemical laboratories, our remote probes tasked with a singular monumental purpose to read the message that Comet Borisov was carrying. Every photon of light captured from its coma was a word. Every spectral line a letter in an alphabet we were just beginning to learn. The light passed through the prisms of our spectrographs would break down into a rainbow barcode, a chemical fingerprint that held the answers to questions we once thought purely theoretical. What elements were present in that distant alien system? What molecules had formed in the protoplanetary disk of another sun? The discovery was more than just an astronomical curiosity. It was a philosophical thunderclap. We were no longer an island. The great ocean between the stars was not an impassable barrier. It was a medium, a dark river, and things could and did drift from one shore to another. Our solar system was not a closed sanctuary, but an open port, and we had just witnessed the arrival of the first foreign ship. The implications were dizzying, branching out in 1,000 directions. If one piece of another solar system could find its way here, then there must be countless others. The galaxy, it turned out, was not a collection of isolated islands. It was an archipelago connected by unseen currents, a cosmic ecosystem where material is exchanged over eons. Bits and pieces of solar systems are constantly being ejected, flung out by gravitational encounters, becoming wanderers, cosmic seeds scattered on the interstellar winds. For billions of years our Earth has been swimming through this river unaware of the messages in bottles, the alien driftwood drifting past us in the dark. Borisov was simply the first one we were equipped to notice. It was a profound and humbling realization. The universe was more connected, more dynamic, and more filled with possibility than we had ever dared to imagine. But with this revelation came the central burning mystery. a mystery that our telescopes were now racing to solve. This piece of another world, this cosmic castaway, was it familiar? Would the chemistry of its birthplace echo our own? Would we look at its composition and see a reflection of our sun's nebula, a sign that the building blocks of solar systems are universal, a common recipe used across the cosmos? Or would we find something else entirely, something strange? An unexpected ratio of elements, an abundance of a molecule that is rare in our own neighbourhood, a chemical signature that speaks of a radically different environment, a different history. Would this messenger from afar tell us that we are in fact typical? Or would its testimony reveal that we are profoundly unusual, the very chemistry that led to our planets, to our water, to us? Is it the galactic standard, or a local anomaly? Comet Borisov held the answer within its vaporizing heart. It was a primordial time capsule not from our own past, but from the past of a place we have never seen, a star we cannot name, and planets we can only dream of. As it blazed through our skies, a temporary guest on an unstoppable journey, it posed the most fundamental question we could ask of the cosmos. When we look out into the universe, are we looking into a mirror, or are we staring into the face of a stranger? The clock was ticking, the data was streaming in, and scientists around the world were about to open the letter to decode this whisper from a distant star, and for the first time read a single isolated sentence from the grand story of the galaxy. Is our cosmic home an island adrift in an eternal empty ocean? Or is it merely one shore in a vast archipelago of stars with celestial driftwood from other worlds, constantly washing up on our beaches unseen? For millennia, this question was the domain of philosophers and poets, a dream whispered into the darkness between the stars. We looked up at the familiar clockwork procession of our own planets, our own comets, our own asteroids, a family of objects bound by gravity to our sun, endlessly circling in a closed, predictable system. The idea that something might break this celestial quarantine, that a rock or a shard of ice forged in the crucible of another star could one day wander into our neighbourhood, was pure speculation. It was a concept so profound, yet so seemingly impossible to prove, that it remained locked away in the realm of imagination. How could we ever hope to spot such a thing? A lone dark traveller, perhaps no larger than a city block, hurtling through the unimaginable blackness at speeds that defy our solar system's placid architecture. It would be a fleeting shadow, a ghost in the machine, gone before we even knew it was there. To find such a needle in the infinite haystack of the cosmos required a fundamental shift in how we watch the skies. For centuries, astronomy was an act of deliberate, focused gazing. A telescope would be pointed at a single star, a specific galaxy, a chosen nebula painstakingly gathering faint light over hours or even nights. This method, while perfect for deep study, left the vast majority of the sky unobserved at any given moment. An interstellar trespasser could easily slip through the net. But the dawn of the 21st century brought with it a new kind of vision. Instead of a patient stare, we developed a restless, sweeping gaze. On the volcanic peaks of Hawaii, a revolutionary sentinel came online, the Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS. It wasn't designed to produce breathtaking portraits of distant galaxies. Its mission was far more urgent, more pragmatic. It was a planetary defense system. Night after night, its enormous digital camera, one of the largest ever built, would scan the entire observable sky, taking thousands of images. The goal was to create a moving picture of our cosmic backyard, to identify any asteroids or comets on a potential collision course with Earth. Powerful computers would sift through a nightly deluge of data, equivalent to thousands of feature-length films, comparing each new image to the one from the night before. The software was engineered to ignore the fixed stars and the distant static galaxies. It was looking for the movers, the wanderers, the tiny points of light that betrayed their proximity by shifting their position against the stellar backdrop. Most of what it found were our neighbours, chunks of rock and ice from the asteroid belt, or icy vagabonds from the Kuiper belt and the Oort Cloud, the deep freeze at the edge of our own solar system. They all followed the same fundamental rules, their paths dictated by the sun's immense gravitational authority. They travelled on closed loops, ellipses that would inevitably bring them back around faithful members of the solar family. For years, the survey scanned, catalogued and watched. They built an unprecedented map of our local space, revealing a far more dynamic and crowded environment than we had ever imagined. Yet the ultimate prize, the visitor from beyond, remained elusive. The mathematical models predicted they should exist. With billions of stars in our galaxy, each likely hosting its own planetary system, with its own comets and asteroids, it was statistically inevitable that some would be ejected during the violent chaos of planetary formation. Trillions upon trillions of these cosmic orphans were thought to be sailing through the interstellar void. But seeing one proving it was another matter entirely. Then, on the 19th of October 2017, something impossible appeared in the data. An astronomer named Robert Verick, combing through the latest Pan-STARRS observations, flagged a faint, unassuming speck of light. It was moving fast, incredibly fast. But speed alone wasn't the anomaly. What set alarm bells ringing across the astronomical world was its trajectory. When astronomers traced its path backward in time, the line didn't curve into a gentle, familiar ellipse around our sun. It was a straight, sharp, defiant line aimed from a distant point in the direction of the star Vega. This object wasn't turning around, it wasn't one of ours. It was a tourist, and it had a one-way ticket out of town. The initial designation was Cold Clinical A 2017 U1. But as the implications sank in as observatories around the world scrambled to train their instruments on the fading visitor, it became clear that this moment demanded a name worthy of its historic significance. The discovery was made in Hawaii, so it was given a name from the native Hawaiian language, a name that perfectly captured the poetic and scientific awe of the moment, Oumuamua. It means a messenger from afar arriving first. For the first time in human history, we knew with absolute certainty that we'd been visited. The dream was real. A piece of another solar system was right here in our home, slipping past our window. The thrill of discovery, however, quickly gave way to a profound and deepening mystery. Our first interstellar guest was nothing like we expected. We had always assumed that the first visitor would be a comet. Comets are the great wanderers of planetary systems, their icy bodies loosely bound by gravity, making them prime candidates for being flung out into interstellar space. And when a comet approaches a star, the heat should sublimate its ice, creating a brilliant glowing halo of gas and dust called a coma, and a magnificent tail that can stretch for millions of miles. It's a spectacular, unmistakable calling card. But as we watched Oumuamua, there was nothing. Silence. Telescopes sensitive enough to detect even the faintest whisper of gas or dust saw only a barren point of light. It was inert dry, and seemingly made of dense rock or metal, so it must be an asteroid then, a wandering piece of a planet shattered long ago in a star system we can only guess at. But that explanation presented its own profound problems. The shape for one was unlike anything we had ever seen. We couldn't see Oumuamua directly, it was far too small and distant, but we could measure the light it reflected from our sun, and that light was behaving bizarrely. Its brightness was fluctuating wildly by a factor of 10 every 7 to 8 hours. For an object to change its apparent brightness so dramatically, it had to have an extreme non-uniform shape. It was tumbling through space, and as it turned, we were seeing wildly different amounts of its surface area. When it was brightest, we were seeing its long side. When it was dimmest, we were seeing it end on. The mathematical models all pointed to one unbelievable conclusion. Oumuamua had to be extraordinarily elongated. It was at least 10 times longer than it was wide-shaped, less like a familiar lumpy asteroid, and more like a cosmic needle or a celestial cigar. No natural object ever witnessed in our own solar system possesses such extreme dimensions. Where could such a strange form have come from? Was it the fragment of a planet torn apart by the tidal forces of its home star? Or was it something else entirely? The questions mounted, each one more perplexing than the last. But the greatest enigma, the clue that would elevate Oumuamua from a mere curiosity to a subject of intense and controversial debate, was yet to come. It was hidden in the subtle nuances of its path. As astronomers tracked its exit from our solar system with painstaking precision, they noticed something that defied the laws of celestial mechanics. Oumuamua was accelerating. It was moving away from the sun faster than gravity alone could explain. The effect was tiny, a gentle, persistent nudge, but it was undeniably there. In our solar system, we see this all the time with comets. As they are heated by the sun, the jets of gas and dust erupting from their surface act like miniature rocket engines, giving them a slight push that alters their trajectory. This phenomenon, known as non-gravitational acceleration, is the very reason comets have tails and comas. It's a visible, well-understood process, but Oumuamua had no tail, it had no coma, it had no visible outgassing of any kind, yet it was being pushed by an invisible, inexplicable force. Here was a visitor from another star, shaped like nothing we had ever seen, acting in a way we couldn't explain. The scientific community was thrown into a state of bewildered excitement. The data was sparse, the time to observe was running out, and the theories began to fly. Perhaps some proposed it was an object made of something exotic, something that would produce an invisible exhaust. Could it be a hydrogen iceberg, an object theorized to form in the coldest parts of giant molecular clouds? As it neared our sun, the frozen hydrogen would boil off, creating a transparent, undetectable plume of gas that could provide the necessary thrust. The problem with this idea is that such an object would be incredibly fragile, likely torn apart by starlight on its long journey through the galaxy. Others suggested it was a nitrogen iceberg, a chip knocked off a Pluto-like dwarf planet in another system. Nitrogen gas would also be difficult to detect, potentially explaining the invisible push. This hypothesis remains a plausible if unproven contender, but the sheer strangeness of Oumuamua, the compounding of one anomaly upon another, led some respected scientists like Avi Loeb of Harvard University to entertain a far more radical possibility. An object that is long, thin, and experiences non-gravitational acceleration from sunlight perfectly fits the description of one specific technology, a solar sail. A solar sail is a theoretical spacecraft propelled by the pressure of starlight itself, pushed by photons in the same way a sailboat is pushed by the wind. Was it possible Loeb and his colleague Shmuel Bialy asked that our first interstellar visitor was not a natural object at all, but a piece of alien technology, a probe, a buoy, or perhaps even the derelict wreckage of a craft from a distant civilization, tumbling silently through our solar system? The suggestion was explosive, sending ripples through both the scientific community and the public consciousness. It was and remains an extraordinary claim. Most scientists believe a natural explanation, however exotic, is far more likely. The principle of Occam's razor suggests we should not multiply entities beyond necessity. We should not leap to aliens when an unknown natural phenomenon might suffice. But the very fact that such a hypothesis could be published and seriously debated by leading astrophysicists speaks to the profound depth of the mystery Oumuamua presented. We simply did not have enough data to rule it out, and that was the ultimate tragedy of this encounter. By the time we understood how truly special our visitor was, it was already leaving. It had rounded the sun and was heading back out into the void at over 196,000 miles per hour. Our most powerful telescopes strained to follow, but soon it was just another faint speck, and then it was gone, swallowed by the darkness. It never even offered us a clear picture, just a set of tantalizing contradictory clues. We had been graced with the presence of a messenger from the stars, and it had whispered a riddle in our ear before vanishing forever into the night. The encounter left a palpable void in its wake, a sense of a monumental opportunity lost. We had touched the interstellar ocean, but only for a moment. The phantom had slipped through our fingers, its secrets unresolved, its origin unknown, its nature a subject of fierce debate. It was a cosmic tease, a single baffling data point that confirmed a magnificent new reality, while simultaneously deepening the mystery. It proved once and for all that our solar system is not an island. Pieces of other worlds truly do traverse the gulfs between the stars, but it also proved how unprepared we were to receive them. Oumuamua ignited a hunger in the astronomical community, a hunger for more data, a hunger for a second chance. The surveys continued their nightly vigil, but now with a new sense of purpose and new alertness. They were no longer just looking for threats from within, they were scanning for visitors from without. The entire scientific world was now holding its breath, waiting. Would another messenger come? And if it did, could we possibly be lucky enough to spot it early enough to truly study it, to unlock the secrets it carried from its alien home? The question hung in the silence of space, a silent prayer for another ghost, another traveller, another chance to meet a piece of a world beyond our own. We would not have to wait long. The wait after Oumuamua was a profound and unsettling silence. For 2 long years, the void offered no encores. The astronomical community, having tasted the impossible, had returned to its familiar rhythms, charting the celestial traffic that belonged to our own sun, our own family of worlds. The fleeting passage of that first interstellar wanderer had become a kind of ghost story, a tantalizing mystery that seemed destined to remain unsolved, a single data point in the immense lonely darkness between the stars. We had been visited, but the messenger had left no note, and so we watched and we waited, scanning the blackness, wondering if we had simply witnessed a once-in-a-lifetime fluke. The breakthrough, when it finally arrived, came not from a mountaintop citadel of glass and steel, nor from a space telescope orbiting high above the distorting haze of Earth's atmosphere. It began in a far more humble setting, a testament to the enduring power of the lone observer, the patient soul with eyes turned skyward. It began in Crimea at a personal hand-built observatory named Margot, with a man who had dedicated his life to the hunt. Gennady Borisov was not a household name in global astronomy. He was a telescope engineer, a devoted amateur whose passion was not just to look at the stars, but to build the very instruments that would bring them closer to craft his own windows into the cosmos. On the night of August 30th, 2019, through a telescope of his own design, Borisov was conducting a routine search for near-Earth comets. It was a painstaking process, a digital form of cosmic archaeology, sifting through fields of ancient light for anything that moved, anything that didn't belong to the static tapestry of distant stars. And there in the constellation Cancer, he found something. A faint fuzzy smudge, an insignificant smear of light crawling almost imperceptibly against the background. To an untrained eye it was nothing, but to a veteran comet hunter it was a whisper of possibility. He carefully logged its position, its faintness, its path. The next night he looked again, and the night after that. The object was real, and it was moving. Following the time-honoured protocol of discovery, he submitted his observations to the Minor Planet Center, the world's official clearinghouse for all things small and solar. This is a daily ritual in astronomy. Thousands of potential objects, asteroids and comets from our own system, are reported catalogued and tracked with meticulous precision. His discovery was initially given a temporary designation, Jesus 34, another file in a vast digital cabinet. But as other observers alerted to the fiend began to track it, a strange and electrifying picture started to emerge. When astronomers plotted its path, feeding the new positions into powerful orbital simulation programs, the computers balked. The numbers they spat out didn't make sense. Every object born of our sun, from the mightiest planet to the smallest pebble, is bound to it by a gravitational leash. Their orbits are closed-loop circles or ellipses. They may wander far out to the frozen frontiers of the Kuiper Belt, but they are fundamentally members of our solar system. They always come back. Their paths are described by a number called eccentricity. For a perfect circle, that number is 0. For an ellipse, it's between 0 and 1. The orbit of this new object, G Borisov 34, was not a circle. It was not an ellipse. The calculations screamed a single, unbelievable conclusion. Its eccentricity was not 1, but a staggering 3.36. This wasn't an orbit. It was an arrow. The object was not looping around our sun. It was screaming past it on a path known as a hyperbola, an open-ended trajectory, a gravitational slingshot that proved it had come from somewhere else entirely. It was not bound by the sun's gravity. It was a tourist, an alien traveller that had blundered into our neighbourhood from the unfathomable depths of interstellar space. The silent void had answered. We had another visitor. The news ripped through the astronomical world like a shockwave. This was not a drill. This was not a ghost. It was happening again, but this time it felt different. This time we were ready. The frantic global race against time began immediately. Oumuamua had caught us by surprise, a thief in the night already heading for the exit by the time we properly saw it. We would not make that same mistake again. A call to arms went out across the planet. At the Gemini Observatory in Hawaii, astronomers abandoned their carefully planned research schedules, a cardinal sin in a world where every second of telescope time is precious and fought for. They pivoted the colossal 8.1-meter mirror a cyclopean eye worth hundreds of millions of dollars towards the tiny, unassuming coordinates that marked the location of this cosmic intruder. On the neighbouring peak of Mauna Kea, the twin Keck telescopes among the most powerful on Earth joined the pursuit. In the Canary Islands, the Gran Telescopio Canarias, the largest single-aperture optical telescope in the world, swung its monolithic 10.4-metre mirror to join the chase. It was an unprecedented mobilization of our greatest scientific instruments, all focused on a single faint speck of light. Every hour was critical. The object, now officially named C2019 Q4, was still inbound, heading towards its closest approach to the Sun. But it was moving at an astonishing speed over 175,000 kilometers per hour, a bullet fired from a gun of galactic proportions. We had a window, a brief few months to study it before it would whip around the Sun and be flung back out into the darkness, disappearing from our skies likely forever. This was our one chance to get a good look, to capture its portrait, to interrogate it, before it vanished back into the interstellar ocean. The first low-resolution images from smaller telescopes confirmed the trajectory. The hyperbolic path was undeniable. It was an alien. But the truly pivotal moment, the revelation that would change everything, came when the data from the Titans like Gemini began to stream in. Astronomers gathered around monitors, their hearts pounding with a mixture of hope and trepidation. What would this second messenger look like? Would it be another bizarre, inert, cigar-shaped enigma like Oumuamua, another sealed letter with no return address, or would it be something else? The raw data frames were processed. Noise was filtered out. Multiple exposures were stacked to enhance the faint signal. And as the final sharpened image materialized on the screen, a collective gasp echoed through observatories across the globe. It was not a dot. It was not a sterile, rocky point of light. The object was fuzzy, wrapped in a ghostly ethereal shroud, and streaming away from it, pushed back by the gentle pressure of our sun's own light and solar wind, was a faint but unmistakable tail. This was no asteroid. This was no cosmic shard of inert rock. This was a comet. A living, breathing comet, complete with a glowing coma, and a delicate tail behaving exactly as a comet from our own solar system would. The discovery was electrifying. The distinction from Oumuamua was immediate and profound. Oumuamua was a mystery precisely because it showed no cometary activity. It was a dead thing tumbling silently through our system, leaving us with more questions than answers. But this new visitor, soon to be formally named 2I Borisov in honour of its tenacious discoverer, was alive with celestial chemistry. That fuzzy glow, the coma, was a cloud of gas and dust material that had been frozen solid for billions, perhaps trillions of years, while wandering the frigid wilderness between the stars. Now, as it neared our sun, it was beginning to warm up. Ices on its surface water, carbon monoxide, cyanogen, were turning directly from a solid into a gas, a process called sublimation. In doing so, they were dragging dust and rock from the comet's nucleus, creating this magnificent glowing atmosphere. It was a celestial blowtorch, and Borisov was actively shedding the very material from which it was made. This was the game changer. Oumuamua had been like finding a sealed ancient bottle on the beach. We could examine its shape, guess its origin, but we could not know its contents. Borisov was that same bottle, but smashed open upon our shores, its precious ancient message spilling out for all to see. For scientists, that glowing gas and dust was not just a beautiful spectacle. It was a treasure trove of unimaginable value. It was a direct physical sample of another solar system, a piece of the primordial cloud that had formed an alien star and its family of unknown worlds delivered right to our doorstep. The excitement that had rippled through the community now erupted into a tidal wave of sheer, unadulterated urgency. The true scientific gold rush was about to begin, because when you have a cloud of gas backlit by the light of distant stars, you can do something extraordinary. You can perform an act of scientific magic known as spectroscopy. By capturing the light that passes through Borisov's coma and tail, and splitting that light into its constituent colours, its rainbow spectrum, we can see the chemical fingerprints of the elements within. Every gas, every atom absorbs and emits light at specific unique wavelengths. They leave tiny dark or bright lines in the spectrum, a kind of cosmic barcode that tells you with astonishing precision exactly what is there. Is there water? Is it the same kind of water we have on Earth? Are there complex organic molecules, the building blocks of life? What is the ratio of carbon to oxygen? Is the stuff that built Borisov in its distant unknown home the same stuff that built our own planet, that built you and me? Suddenly the questions that Oumuamua had left us with questions we thought we might never answer seemed within our grasp. This was no longer a passive observation of a passing oddity. This was an active interrogation, a celestial autopsy. Every major telescope on the planet, including the Hubble Space Telescope, was now pointed at this single transient visitor. The race was no longer just to confirm its existence, but to dissect it, to tear it apart photon by photon, to read the chemical story written in its vaporizing heart. The clock was ticking louder than ever. Every observation, every spectral line captured was a priceless datum, a clue to a puzzle far larger than our own solar system. We had our messenger. It was speaking to us not in riddles, but in light. And the entire world of science was leaning in desperate to translate. And so the chase across the inner solar system was over. The physical pursuit, the raw act of pointing our telescopes and tracking this celestial fugitive had reached its climax. But the true hunt, the intellectual and spiritual quest to understand what Borisov truly represented, was only just beginning. For this was the moment we moved beyond simply watching a ghost and began the delicate, almost sacred process of interrogating it. The light that had travelled for millions, perhaps billions of years from an unknown hearth was now arriving at our doorstep, and within that faint ancient glow were the answers we craved. It was time to put Borisov on trial, to cross-examine its very soul, using the most powerful tool in the astronomer's arsenal, light itself. Deep within the cooled, silent chambers of Earth's greatest observatories, from the high, arid plains of the Atacama to the volcanic peaks of Hawaii, an invisible net of human ingenuity was closing around the comet. The collected photons, each one a tiny messenger from the interstellar void, were being channeled not into cameras to create a simple portrait, but into the intricate hearts of spectrographs. Here light ceases to be just a picture, it becomes a language. Passed through a cosmic prism, the comet's single pale beam is shattered, unfurled into a magnificent rainbow of constituent colours, a spectrum. But this is a broken rainbow, a barcode of creation slashed through with fine, dark lines of absence. Each missing sliver of colour, each absorption line, is a fingerprint left behind by a specific atom or molecule that has stolen that precise wavelength of light. This is where the magic happens. This is where we learn to read the comet's mind. It is a painstaking process, a form of celestial archaeology where we decipher the chemical hieroglyphs written in starlight, each symbol telling a part of a story that began in utter alienness. The first signals to emerge from the noise were familiar, almost comforting. A distinct pattern of missing light appeared in the infrared, a signature so common, so fundamental to our own world, that its presence in this interstellar traveller sent a shock of recognition through the scientific community. It was the unmistakable fingerprint of water, H2O. The molecule of life of our oceans, of our own bodies, was sublimating from the nucleus of Borisov, gushing into the vacuum of space as a vast invisible cloud. For a moment, the immense gulf between star systems seemed to shrink. This object, born in a place we may never see, was built from the same primordial ingredient that carved our canyons and fills our cells. It confirmed a profound and beautiful suspicion that the raw materials for worlds like ours are not a local anomaly. They are a cosmic standard. The universe, it seemed, uses a common recipe book. The water ice locked within Borisov's core was a chemical bridge, a tangible link connecting their solar system to ours. It was a reminder that across the galactic expanse the laws of physics and chemistry are constant, weaving the same essential tapestry everywhere. We could almost imagine the snowflakes that condensed in its youth, drifting down through a protoplanetary disk lit by a foreign sun. This initial discovery was a moment of profound connection, a handshake across an unimaginable void. But this handshake was just the beginning of the conversation, and as we listened more closely, the alien accent began to show. The teams dug deeper into the spectrum, past the bold signature of water, searching for the fainter whispers, the more subtle clues, and that is when they found it. a signature so strong, so overwhelmingly dominant it completely rewrote our understanding of this visitor. It was the deep triple bond shadow of carbon monoxide, CO. In our own solar system, comets contain carbon monoxide, of course. It's a common simple molecule, a building block of the cosmos. But in our comets, it exists as a trace component, a minor ingredient in a recipe dominated by water ice. We might find one molecule of CO for every 100 molecules of water. It's the seasoning, not the main course. Borisov, however, was saturated with it. The data streaming back from the telescopes was unambiguous. The sheer abundance of carbon monoxide was staggering, dwarfing the amount seen in any comet native to our solar system. In some readings, it was almost as plentiful as water itself. This was not a subtle difference. This was a fundamental schism. This was Borisov screaming its otherness across the void. To understand the gravity of this discovery, you have to understand the nature of carbon monoxide ice. It is an exceptionally volatile substance, a true phantom of the cold. Water ice, the kind that makes up the bulk of our own comets, can remain frozen solid at relatively warm temperatures around -100 degrees Celsius. But carbon monoxide needs the bone-chilling cold of the deepest space to remain a solid. It turns to gas at temperatures below -250 degrees Celsius, just a few tens of degrees above absolute zero, the point where all molecular motion ceases. This molecule is the frozen breath of the interstellar abyss. Its extreme volatility means it can only form and survive in the most frigid, most remote regions of a solar system. Our own comets, those from the Oort Cloud, are born in the cold, dark suburbs of our Sun, but the sheer quantity of CO in Borisov suggested something more extreme. It was not born in the suburbs. It was forged in a celestial Siberia, a place far colder, and likely much more distant from its parent star than the birthplace of our own comets. Imagine two snowballs packed by two different children in two different worlds. One from our Oort Cloud is made mostly of dense wet snow, our water ice. Sprinkled within it are a few flakes of fine dry powder, the carbon monoxide. Borisov's snowball, however, was packed from a different kind of winter. It was an almost equal mix of that wet snow and the fluffy powder, creating a substance with a completely different nature, one that would begin to vaporize in even the slightest warmth. This single chemical discrepancy told a richer story than any photograph ever could. It was the first tangible clue, the first hard piece of evidence about the environment of its home. The star it orbited was perhaps much dimmer than our Sun, a faint red dwarf, whose habitable zone would be huddled close, leaving its outer realms in a permanent deep freeze. Or perhaps Borisov was born in a much larger, more massive protoplanetary disk, where the frost line for carbon monoxide was pushed out to truly epic distances from its stellar furnace. The possibilities began to branch, each one more tantalizing than the last. The overabundance of CO was a chemical ghost, a spectre of the profound cold from which it was exiled. It was a message written in the language of thermodynamics about the architecture of another star's family of worlds, and the revelations kept coming. As the spectrographs continued their silent, relentless interrogation, more of Borisov's ingredients came to light. The teams detected the telltale green glow of diatomic carbon C2, a molecule formed when more complex carbon chains are broken apart by sunlight. This was expected. It's the source of the emerald atmosphere, the coma that gives comets their ethereal, ghostly beauty. They found the faint but distinct signature of the cyanide radical CN, a molecule that sounds menacing, but is in fact a standard component of comets everywhere, a key player in the prebiotic chemistry that may have seeded early Earth with the building blocks of life. These similarities were just as important as the differences. They painted a picture not of complete and total alienness, but of a subtle variation on a universal theme. The universe was not using a different recipe book for Borisov's system. It was just emphasizing different chapters. The basic grammar of solar system formation, ice dust and simple organics was the same. What differed was the dialect, the local environmental conditions that favoured one ingredient over another. But even the dust, the very grit and soil of this interstellar traveller, told its own unique tale. By analysing how the comet's dust scattered sunlight, astronomers could deduce the nature of the grains themselves. The dust in our solar system's comets is a fluffy mixture, porous aggregates of silicates and carbon like cosmic dust bunnies. Borisov's dust seemed different. It was composed of very fine, compact pebbles, perhaps a millimetre in size, more like sand than soot. This subtle distinction hints at a more dynamic turbulent youth. Perhaps the disk from which Borisov formed was a more violent place, where dust grains were churned and processed more intensely, colliding and compacting into these dense little pellets before being frozen into the body of the comet. It was another brushstroke in the portrait of its birthplace, adding a texture of turbulence and activity to the canvas of extreme cold. Every photon was now a puzzle piece. The water told us of universal chemistry. The carbon monoxide whispered of an impossibly cold nursery. The nature of its dust spoke of a dynamic and active adolescence. We were staring at a molecular fossil, a perfectly preserved, flash-frozen sample of the gas and dust that existed in another solar system when it was forming billions of years ago. Our own comets provide us with a similar window into our own past, allowing us to study the conditions of our solar system's infancy. But Borisov was different. It was a single page torn from a galactic library of 1 billion books, and we had just one chance to read it before it turned and flew away forever. For the first time, we weren't looking at a simulation or a theoretical model of what another planetary system might be like. We were holding a piece of one in our hands, chemically speaking. We were analysing its atomic and molecular DNA, and its genome was telling us a story of a place that was at once profoundly similar and yet deeply, fundamentally different from our home. The implications were dizzying. The specific ratio of carbon monoxide to water, the unique composition of its silicate dust, the relative abundances of cyanide and other trace molecules, this was more than just a list of ingredients. This was a formula, a recipe for planet formation under a different star. By comparing this alien formula to our own, we could begin to understand the full spectrum of possibility for how solar systems are built. Are systems rich in carbon monoxide more likely to form gas giants in their outer reaches? Does the nature of the dust affect how quickly rocky planets can assemble? These were no longer abstract questions for computer models. Borisov had delivered the first piece of ground truth, a physical data point from another world that could anchor all our theories. It was a cosmic anchor thrown across the interstellar ocean, allowing us to steady our vessel of knowledge as we chart these unknown waters. The turning point was complete. Borisov was no longer just a speeding point of light and astronomical curiosity. It had become a messenger, a time capsule carrying a detailed chemical blueprint from a neighbouring star. The faint glimmer we had chased across the sky had been given a voice, and it was speaking of its origins in the language of chemistry. The story was no longer just about its incredible journey, but about the home it had left behind. We now knew with a certainty that was once the stuff of science fiction, the composition of the primordial cloud from which its family of planets was born. We had tasted the air of another nascent solar system, and that taste was unique. The molecular signature was as clear as a fingerprint left at a crime scene. The question was no longer what Borisov was made of. We had the list of parts. The new, far more profound mystery, the one that would consume us next, was piecing together those parts to envision the whole. What kind of star, what kind of system, what kind of cosmic environment could possibly assemble a creature like this? The chemical clues were all on the table. It was time to become detectives, to follow this trail of molecules back across the light years to find the nature of its sun. With its chemical soul laid bare, the ghost was no longer a complete stranger. The alien ice, the primordial dust, the captured gases, they were the words. But what was the story they were trying to tell? For the teams of scientists who had captured its fleeting whisper, the revelation of Borisov's composition was not an ending, but the explosive beginning of the greatest detective story in modern astronomy. The evidence was on the table, a spectral fingerprint from another star. Now the real interrogation could begin. The question was no longer simply, what are you, but where did you come from? And what in the name of all worlds could have happened there to cast you out into the lonely eternal darkness between the stars? This was a new kind of archaeology, a cosmic forensics. We couldn't visit the scene of the crime, the birthplace of this orphan world. It was likely hundreds, if not thousands of light years away, a needle of a star lost in the haystack of the Milky Way. But we had a piece of it right here in our own backyard. Borisov itself was the artifact, a frozen, tumbling time capsule. Every molecule within it was a clue. Every photon of light it reflected was a testament to the environment that forged it. Scientists began a process of reverse engineering, not a machine, but an entire solar system they had never seen. They took the data, the strange abundance of carbon monoxide, the familiar signature of water, and began to build a profile, a police sketch of a place we can only dream of visiting. The most glaring piece of evidence was that carbon monoxide. In our own solar system, this volatile gas freezes into ice only in the most frigid distant reaches far beyond Neptune, in the cold, dark suburbs of the Kuiper Belt and the Oort Cloud. For Borisov to be so rich in it, for this gas to be a fundamental building block of its very being, it must have been born in a place of profound cold. This wasn't just a comet that formed in the outer lane of its system. This was a creature of the extreme deep freeze. The data painted a picture of a nursery shrouded in a biting, unimaginable chill, a place where the light of its parent star was a distant, feeble glow, offering little in the way of warmth. Imagine a protoplanetary disk, that spinning platter of gas and dust, from which planets are born, but one far larger and colder than our own. Out there on its outermost edges, where starlight is but a rumour, the carbon monoxide frost line would be the dominant frontier of creation. This is where Borisov likely first coalesced a tiny clump of alien frost and dust, in a realm of perpetual twilight. This clue immediately began to narrow down the list of suspects for its home star. A bright, hot, sun-like star would likely have vaporized such delicate ices, pushing that frost line too far out, making a carbon monoxide-rich body less probable. Instead, the profile began to point towards a cooler, dimmer, and far more common type of star, a red dwarf. These are the quiet, unassuming runts of the stellar litter, outnumbering stars like our Sun by a factor of 10 to 1. They sip their fuel, slowly burning for trillions of years, their light a soft, ruddy crimson instead of a brilliant yellow-white. A solar system around a red dwarf would be a profoundly different place. The habitable zone, the Goldilocks region where liquid water could exist, would be huddled incredibly close to the star for warmth. But its outer regions, the cometary nursery, would be a vast and deeply frozen expanse, a perfect factory for creating objects just like Borisov. The theory was elegant, statistically likely, and fit the chemical evidence perfectly. For the first time, we had a plausible image of Borisov's home, not a specific star on a map, but a type of home. We could almost feel the cold seeping from its nucleus, the memory of a dim red sun hanging in a black alien sky. But forming in the cold is only one part of the story. A comet born in the outer fringes of its system doesn't just decide to leave. Something must have compelled it. Something must have given it the astonishing velocity needed to escape the gravitational grip of its parent star and begin its million-year pilgrimage. There had to be a cataclysm, a moment of immense gravitational violence. The prime suspect for that violence, a giant planet. In this developing picture of Borisov's home system, a colossal world now took shape, a gas giant perhaps many times the mass of our own Jupiter, orbiting its red dwarf star in a wide sweeping path. Planetary systems are not the serene clockwork mechanisms we once imagined. Especially in their youth, they are chaotic, brutal arenas. Young planets migrate their orbits, shifting and jostling for position, in a gravitational dance that can last for hundreds of millions of years. In this cosmic mosh pit, smaller bodies like comets and asteroids are treated like mere shrapnel flung about by their larger siblings. We can now visualize the final violent moments of Borisov's life at home. It was likely just one of billions of icy bodies orbiting peacefully in the silent frozen dark. Then the great disruptor arrived. The gas giant in its majestic lumbering orbit swung through this cometary field. Its gravity, a force of unimaginable power, acted like a cosmic slingshot. Borisov, caught at just the right angle, was ensnared by this invisible tether whipped around the giant planet and accelerated to a terrifying speed. It was a gravitational pinball machine, and Borisov hit the jackpot, achieving a velocity that its own star could no longer contain. It was ejected, shot out of its own solar system like a cannonball condemned to wander the great, empty ocean of interstellar space. It was an exile, not a pioneer. A piece of flotsam from a planetary shipwreck carrying the chemical memory of a home it could never return to. This emerging biography was breathtaking, a story of quiet creation, followed by sudden calamitous expulsion. And it made Borisov's arrival in our system all the more profound. It wasn't just a rock, it was a refugee. As the comet reached perihelion, its closest approach to our Sun, the observations were frantic, a rush to capture every possible scrap of data before it began its long journey back out into the void. Then as it rounded the Sun and began to recede, the nature of the mission changed. The urgency of discovery was replaced by the patient diligence of a farewell tour. Every week it grew a little fainter, every month a little more distant. Telescopes around the world and in orbit kept their vigil tracking this fading ember as it climbed back up out of the Sun's gravity well. The story, it seemed, was largely written. We had its composition a plausible origin story, a dramatic tale of its ejection. All that was left was to watch it disappear, a final wave goodbye, as it dissolved back into the galactic background from which it had so briefly emerged. But Borisov had one last shocking surprise for us. It wasn't going to leave quietly. In March of 2020, long after its closest encounter with the Sun, astronomers monitoring the comet noticed something strange. It suddenly, inexplicably brightened. Comets can have outbursts, of course, when pockets of volatile ice are exposed to sunlight and erupt in a plume of gas and dust. But this was different. It was happening far from the Sun, where the thermal stresses should have been decreasing, not increasing. The brightening was sharp, a flash of activity that put the entire community on high alert. Something was happening deep inside the comet's nucleus. The call went out. Every available eye was turned back to the fading visitor. And the Hubble Space Telescope, our most powerful window on the universe, was tasked with taking a closer look to perform an emergency diagnosis on our ailing interstellar patient. The images that came back were stunning and heartbreaking. Hubble's crystalline vision revealed that Borisov was no longer a single solid object. The sharp, star-like point of its nucleus now had a ghostly twin. A significant fragment had broken away from the main body, drifting alongside it, like a lifeboat from a sinking ship. Borisov was disintegrating. The visitor from another star system, the survivor of a million-year trek through the barren wilderness of interstellar space, was falling apart. It had weathered the unimaginable cold and radiation of the void, only to be mortally wounded by a brief gentle brush with our Sun's warmth. The revelation sent a shockwave through the scientific community. The questions came thick and fast. What could have caused this? Was it a delayed thermal shock? A deep fracture from its solar passage that had only now worked its way to the surface? Did the nucleus spin itself apart, cracking under the torque from its outgassing jets? Or was Borisov simply fragile? This single observation forced a radical re-evaluation of its entire nature. We had imagined it as a hardened survivor, a dense, resilient bullet that had endured an epic journey. But perhaps that was wrong. Perhaps the very conditions that made it so unique, its formation in the extreme cold, also made it incredibly delicate. Think of a snowball packed loosely in gentle cold versus an ice cube frozen solid in a deep freezer. Borisov may have been more like the former, a fluffy agglomeration of ices and dust barely held together. In the frigid quiet of interstellar space, this lack of structural integrity didn't matter. There was nothing to disturb it. But the gentle, persistent heating from our Sun, followed by the slow recooling as it moved away, was like repeatedly warming and chilling a piece of fragile crystal. Eventually, the stress became too much. A crack appeared, and a piece fell away. This was a celestial shipwreck occurring in agonizing slow motion before our very eyes. The discovery added a poignant, urgent new layer to the observations. We were no longer just watching a comet leave. We were watching it die. Its fragmentation was a tragic, beautiful, and profoundly informative event. It suggested that interstellar comets might be fundamentally different from the ones born in our own system. Our comets are survivors of a much more turbulent youth, repeatedly baked and stressed by their orbits around our powerful Sun. The weak ones were filtered out long ago, broken apart and scattered. The ones we see today are the tough ones, the veterans. Borisov, on the other hand, was a pristine relic. It had never been this close to a star before. This was its first and only trial by fire, and it was failing. It was like a deep-sea creature perfectly adapted to the crushing pressure and cold of the abyss suddenly brought to the surface, whether warmth and light or a death sentence. The implications were immense. If Borisov was representative, then the galaxy could be filled with these incredibly fragile, ghost-like objects drifting between the stars. They are the untouched raw material from the birth of other solar systems so delicate that they can only be studied if they happen to wander into our path. And even then, the very act of observing them, of welcoming them with our sun's light, could be what destroys them. This paradox was not lost on the astronomers watching its slow demise. They were witnesses to a unique form of cosmic destruction, a process that revealed more about Borisov's true character than months of spectral analysis ever could. The comet was no longer just a messenger. It was a martyr sacrificing its own physical integrity to give us one final crucial piece of the puzzle. As it continued its retreat, now a wounded traveller trailing debris, the vigil became even more sombre. How much of it would survive to reach the darkness again? Would it crumble into a cloud of dust, its story dissolving into nothingness? Or would a core fragment endure, carrying the scars of its visit to our system, onward for another million years, a battered veteran for another star's children to find? The fading light from this disintegrating alien held the answers. Its final act was not one of silent departure, but of dramatic, unexpected self-destruction. And as it tumbled back into the abyss, fainter and more broken with every passing day, it left us with a deeper mystery than when it first arrived. It left us to wonder about the resilience of life-bearing worlds, about the violent beginnings of all solar systems, and about the countless other fragile messengers, each carrying its own ghost of a story still wandering unheard in the great silent dark. With its path through our own solar family meticulously mapped, the great cosmic detective story could truly begin. We had tracked the intruder's every move from the moment it breached our celestial borders, calculating its velocity, its trajectory, its point of closest approach to our sun with breathtaking precision. The evidence was irrefutable. Borisov was an exile, a wanderer cast out from another star system, on a journey that had lasted for an unthinkably long time. But knowing that it came from the abyss is a profoundly different thing from knowing where. Its journey through our system was but the final fleeting chapter of an immense, silent epic written across the void. To find its home, we would have to learn to read the ghost of its path, a trail not of ice or dust, but of pure gravitational memory. We needed to rewind the cosmic clock. This is a task of almost unimaginable complexity. It is not like tracing a line back across a static map. You cannot simply point your finger in the direction Borisov came from and expect to find its parent star waiting there. The galaxy itself is a living, breathing, dynamic entity. Everything in it moves. Everything. The sun. Our entire solar system is hurtling through space at over 500,000 miles per hour, orbiting the galactic center in a grand 230 million year waltz. And so is every other star. They drift, they weave, they are pulled by the gravitational tides of the Milky Way's spiral arms and the immense unseen anchor of dark matter at its core. Over the millions of years Borisov likely spent in transit, its home star would have moved potentially by hundreds of light years from the position it occupied at the moment of the comet's violent expulsion. Trying to find its origin is like trying to trace a single specific raindrop back to the cloud it fell from after both you and the cloud have been carried for miles by a relentless hurricane. The coordinates of the past are gone seemingly forever. To even attempt such a cosmic reconstruction required a map. Not just any map, but a four-dimensional one, a map of not only where the stars are, but where they're going and how fast. For decades, such a map was pure science fiction. But we live in an era of wonders. We have such a map. Its name is Gaia. The European Space Agency's Gaia Observatory is arguably the most ambitious cartography project in human history. From its vantage point in space, it has spent years watching the stars, measuring the positions, distances, and proper motions of nearly 2 billion of them, with a precision so exquisite it can detect the width of a human hair from over 1,000 miles away. Gaia did not just give us a static photograph of our galactic neighbourhood. It delivered the script of its motion, a dynamic blueprint of the celestial dance. For the astronomers hunting Borisov's home, the Gaia data catalogue was not just a tool. It was the sacred text, the only key that could possibly unlock the door to the past. The first step was to build a universe in a box. Using the Gaia data, teams of astrophysicists constructed the most faithful digital twin of our corner of the Milky Way ever conceived. Inside supercomputers, billions of stars, each one a real star from the catalogue, were set in motion according to the laws of gravity. Their pasts and futures could be simulated, the grand ballet of the local stellar cluster played forwards and backwards at will. This was their celestial time machine. Into this digital ghost of the galaxy they placed Borisov. They took its vector as it entered our solar system, its precise speed and direction of travel. The cold hard numbers gleaned from months of observation, and they hit rewind. The phantom of Borisov began its journey backwards, a lonely point of the light streaking in reverse through the simulated cosmos, its path a ghostly thread unwinding through space and time. Simultaneously, the simulation wound back the clock for all the stars. The digital suns began to move, tracing their orbits back through millennia, centuries, hundreds of thousands of years, and finally millions of years. The search was on. The algorithm was hunting for a single critical moment and intersection. It was looking for a star whose simulated journey backwards through time would bring it incredibly close to Borisov's own phantom trail. A cosmic rendezvous in the distant past. The computer churned through petabytes of data, calculating trillions upon trillions of interactions. Each star was a suspect in this galactic manhunt, and each one had to be given an alibi, or identified as a person of interest. The criteria for a match were unforgivingly strict. The star and the comet's ghost had to pass within a few light years of each other, a mere stone's throw on the galactic scale. Crucially, their relative velocity at that point of intersection had to be very low. After all, Borisov had to have been moving slowly relative to its parent star just before it was ejected. A high-speed flyby would mean nothing. They were looking for a plausible point of origin, not a random near miss in the cosmic traffic. The first runs of these immense simulations produced a dizzying list of potential candidates. Thousands of stars at various points in the last 10 million years had crossed paths with Borisov's unwinding trajectory. The initial excitement was tempered by the sheer volume of possibilities. The search area was vast, the suspects numerous. It felt like trying to solve a crime with thousands of fingerprints at the scene all overlapping. But the detectives of the cosmos had another tool at their disposal, a way to narrow the field. They began to apply more subtle physical constraints. They asked a simple question: what kind of event could eject a comet like Borisov? It couldn't be a supernova. That would have utterly vaporized it. It had to be a gravitational interaction, a slingshot. This meant the parent system likely contained a massive planet, a gravitational bully capable of flinging a small icy body out of its orbit with enough force to achieve interstellar escape velocity. This crucial insight allowed the researchers to filter their list of suspects. They began to prioritize stars known or suspected to host giant planets. They looked for systems that were dynamically young and unstable places, where planets might still be migrating and jostling for position, creating the kind of gravitational chaos that leads to ejections. The list of thousands shrank to hundreds, and then to a few dozen prime candidates. Each one represented a possible home, a potential cradle for our interstellar visitor. There was a G-type star like our own Sun, but much younger, its planetary system still a violent, chaotic construction site. There was a pair of stars locked in a tight gravitational embrace, a binary system where the competing pulls of two suns could easily perturb a comet from its distant orbit and send it careening into the void. Each possibility was tantalizing a doorway to another solar system we could almost picture. But without more evidence, it was still just speculation. They needed a tiebreaker. They needed a smoking gun. And they had one. It had been with us all along, hidden in the light of the comet itself. It was Borisov's chemical fingerprint. As we established earlier, this was no ordinary comet. Spectroscopic analysis had revealed a composition unlike almost any comet from our own Oort Cloud. Specifically, it was extraordinarily rich in carbon monoxide. This volatile gas, which freezes at incredibly low temperatures, was present in amounts far exceeding what we see in our native comets. Furthermore, Borisov appeared to be a pristine object. It had likely never made a close pass by its own star, preserving the raw primordial materials from which it was born. This unique chemical signature was the final decisive clue. It was the DNA evidence that could link the suspect to the scene of the crime. The question was no longer just, which star did Borisov pass close to? It was now, which star system provides the perfect environment to build a comet? This rich in carbon monoxide, and then eject it so gently that it remains intact. Suddenly, one type of star system jumped to the very top of the list, a red dwarf. Red dwarfs are the most common stars in the galaxy, but they are vastly different from our Sun. They are small, they are cool, and they are incredibly long-lived. Because a red dwarf is so much dimmer and cooler than a star like our Sun, the frost line in its protoplanetary disk, the line beyond which volatile compounds like carbon monoxide can freeze into solid ice, is much, much closer to the star itself. This means that a comet like Borisov, packed with frozen carbon monoxide, could form in a region of its home system that was still relatively dense with material, allowing it to grow large and robust. In a Sun-like system, that same region would be far too warm. A comet would have to form much farther out in the diffuse icy fringes where material is scarce. The high carbon monoxide content of Borisov was a screaming advertisement for a red dwarf origin. The simulations were run again this time with a new powerful filter. The computers sifted through the shortlist specifically looking for red dwarf stars that met the strict trajectory criteria. The field of suspects collapsed. Dozens became a handful became 3, then 2, and then finally 1. One candidate system matched every single criterion with an astonishing degree of confidence. The models converged, the data aligned. After years of searching after running simulations that encompassed millions of years and billions of stars, the astronomers had found it. They had found Borisov's cosmic address. The system is known as Kruger 60. Located just 13 light-years away from us in the constellation of Cepheus, it is a binary system composed of 2 red dwarf stars orbiting each other. It is old, it is stable now, but the models showed that its past was likely anything but. The backwards projection was undeniable. Approximately 1 million years ago, the phantom of Comet Borisov passed within a whisper of the Kruger 60 system, moving at a velocity so slow it was essentially at rest relative to the 2 stars. It was the perfect match. The manhunt was over. With this stunning revelation, we can do more than just point to a star in the sky. We can reconstruct the crime. We can travel back 1 million years and witness the final dramatic moments of Borisov's life in its own home. Picture it. A cold, dark world orbiting 2 dim red suns. Out in the icy blackness much farther than the orbit of Neptune in our own system, a small, unassuming chunk of ice and rock has been circling peacefully for billions of years. This is Borisov. Its existence has been quiet, uneventful. But elsewhere in the system, a gravitational drama is unfolding. A larger planet, perhaps a super-Earth or a mini-Neptune, has been slowly, inexorably migrating in its orbit, its gravitational influence reaching out like an invisible hand. Over countless orbits, its path brings it into alignment with the tiny frozen comet. It does not collide. It does not need to. Gravity is all that is required. For one terrifying final moment, Borisov is caught in the giant planet's gravitational well. It is a cosmic slingshot. The comet is whipped around the planet, its orbital energy magnified enormously. Its allegiance to the 2 red suns of Kruger 60 is violently severed. In a silent, cataclysmic instant, it is flung away, accelerated beyond its home system's escape velocity. It has been given a one-way ticket to the stars. From that moment on, it was an exile, a castaway. It sailed through the absolute darkness between the stars, a realm of unimaginable emptiness and cold for 1 million years. Its journey was a straight line through the void, a testament to the laws of motion. It coasted on the momentum of its violent birth as an interstellar object, a tiny frozen message in a bottle thrown from the shores of another world. Its long, lonely voyage finally ended when by pure chance it drifted into the gravitational territory of our own sun. We were simply the next port of call on an infinite journey. Finding its origin at Kruger 60 does something profound. It transforms Borisov from a mere astronomical curiosity into an emissary. It is no longer an anonymous wanderer, but a tangible piece of a specific named place. We can look up at the constellation Cepheus and know with a high degree of certainty that we are looking in the direction of the hearth from which this celestial spark flew. We have closed the case on its origin. We have written the first chapter of its epic biography. But in solving one mystery, we have opened the door to a much larger, more tantalizing one. The same simulations that identified Kruger 60 as Borisov's birthplace also carry a staggering implication. The gravitational dynamics that ejected Borisov are not rare. In fact, they are likely a common, even mundane feature of planetary system formation, especially around the countless red dwarf stars that populate our galaxy. If a world like Kruger 60 can cast one of its children out into the void, then it has almost certainly cast out many more. And there are billions of stars like Kruger 60. The galaxy, it seems, may be overflowing with these homeless wanderers. What does it mean to live in a cosmos that is not a collection of isolated islands, but a dynamic, interconnected ocean where pieces of one solar system constantly wash up on the shores of another? How many more messengers from distant suns are hurtling through the darkness right now on a trajectory that will one day bring them into our own backyard? The discovery of Borisov was not an end. It was a beginning. It was the moment we realized the universe has been knocking on our door all along. We just needed to learn how to listen. And so it is gone. Fading back into the infinite night from which it came, Comet Borisov becomes a ghost. A whisper of light, a memory imprinted not on the sky, but on us. We followed its fleeting passage, a frantic chase against the unyielding clockwork of celestial mechanics, and now its arc carries it away forever beyond our reach. There will be no second look, no follow-up visit. The encounter is over. But as this tiny emissary dissolves into the stellar tapestry, its true journey, its true impact is only just beginning. It has left behind more than a trail of dust and gas. It has left a permanent change in the architecture of human thought. Before Borisov, the concept of other solar systems was a grand but abstract truth. We could see their stars in further presence of their planets through subtle dips in starlight, or the gravitational wobble of a distant sun. We built intricate models, beautiful theories of how these alien worlds might form of the chemistry that might swirl in their primordial disks. They were destinations on a map of pure intellect, magnificent but untouchable. We were cosmic islanders aware of other continents, but with no ship and no message in a bottle to prove they were real. We lived by inference, by the elegant logic of physics that suggested if planetary formation happened here, it must happen elsewhere. Borisov shattered that isolation. It was the message, the ship, and the exotic cargo all in one. For the first time in the history of our species, we held a piece of another star's family in our hands. Not a theory, not a simulation, but a physical artifact, a tangible sample delivered directly to our doorstep. Every photon captured by our telescopes, every spectral line analysed, was a direct conversation with a place we will never see. This was no longer speculation. It was geology, it was chemistry, it was forensics on a galactic scale. The abstract map of the cosmos suddenly had a real physical landmark. The water we found locked in its ice was not just water, it was confirmation of a universal solvent, the same molecule that fills our oceans and our cells, forged in the crucible of a completely separate star system. It was a profound statement of cosmic unity, a hint that the fundamental ingredients for life as we know it are not a local specialty, but a galactic standard. This simple molecule H2O became a bridge of shared chemistry, spanning the light years, transforming our search for life from a hopeful prayer into a statistical probability. The building blocks are out there. Borisov proved it. Yet it was the comet's strangeness that delivered an equally vital lesson. The astonishing abundance of carbon monoxide, far more than any comet from our own Oort Cloud, was a chemical telegram from its birthplace. It spoke of an environment profoundly different from our own, likely born in the frigid carbon-rich outer darkness of a red dwarf star. This wasn't just another version of our own solar system. This was a glimpse into an entirely different evolutionary path, a different set of rules for building worlds. It told us that the universe is not just filled with copies of our home. It is an endless laboratory of cosmic experimentation. This single dirty snowball has therefore given us a crucial piece of the puzzle, a cosmic Rosetta Stone that helps us decipher the light from distant exoplanets. When the James Webb Space Telescope stares into the atmosphere of a world orbiting a star like TRAPPIST-1, it sees chemical fingerprints. Before Borisov, we had to compare that data to models based solely on our own solar system. Now we have a vital calibration point. We have direct physical evidence for the chemical diversity that exists, allowing us to interpret that alien atmospheric data with newfound confidence. We can now ask sharper questions. Does that planet's atmosphere suggest a formation history more like our own, or one more akin to Borisov's parent system? The comet has fundamentally shifted planetary science from a monologue into a dialogue. We are no longer just talking to ourselves, projecting our own history onto the cosmos. The universe, through Borisov, has started talking back. And this conversation demands a new generation of explorers. Borisov's visit was a wake-up call, a stunning demonstration of both the opportunity and our unpreparedness. We were observers scrambling to point our existing telescopes at a target that appeared and vanished in a flash. We were passive witnesses to a historic event. The question that now electrifies space agencies and engineering labs around the world is, next time can we do more? Can we be ready not just to see, but to touch? Imagine a new kind of mission, a celestial ambush, predator of science. A probe perhaps like the European Space Agency's Comet Interceptor, launched not to a specific destination, but to a quiet, stable point in space, a gravitational eddy like Lagrange Point 2. There it would lie in wait dormant for years. Its electronic sensors would be tuned to the sky, listening for the alert from survey telescopes on Earth, the cry that another interstellar traveller has been spotted on an inbound trajectory. When that alarm sounds, the probe awakens. Its mission, a high-speed chase to catch a ghost. The calculations would be breathtakingly complex. To intercept an object moving at hundreds of thousands of kilometers per hour on a hyperbolic path requires a perfect trajectory, a slingshot maneuver around the Earth or Moon, and an engine burn executed with unimaginable precision. The probe would not be chasing the visitor out of our system, but racing to meet it head-on as it plunges toward the Sun. The encounter would be fleeting, a violent high-velocity flyby lasting perhaps only a few hours. In that tiny window, the probe would unleash a torrent of scientific inquiry. It would fly through the coma, that tenuous atmosphere of dust and gas, its mass spectrometers tasting the very essence of another solar system. It would deploy sub-probes to get even closer, mapping the nucleus, analysing the jets of vapour erupting from its surface as it feels the sun's warmth for the first time. We would not just be analysing its chemistry from afar, we would be feeling its texture, weighing its molecules, taking its temperature. We would be performing an autopsy on a body from another star. The technological leap required for such a mission is immense. It demands advances in autonomous navigation, because the light speed delay would make real-time human control impossible. It requires instruments that can perform complex science in a chaotic, high-speed environment. But the dream of such a mission is no longer science fiction. It is the direct, tangible legacy of Gennady Borisov's discovery. He didn't just find a comet. He created a new destination, a new and compelling reason to push our engineering to its absolute limits. We are no longer content to wait for messages in a bottle to wash ashore. We are now building the ships to sail out and meet them in the open ocean. This shift from passive observation to active pursuit reshapes our entire cosmic perspective. For millennia, we have been defined by our celestial neighbourhood. Our myths, our calendars, our science, all were born from the predictable rhythmic dance of our sun, our moon, and our planets. It created a comforting, if illusory, sense of cosmic order and isolation. Our solar system was a walled garden, a self-contained unit, and everything beyond was simply a static, painted backdrop. Borisov breached the wall. It proved that the space between the stars is not an empty void, but a dynamic transport system. It is an ocean with currents of gravity and rivers of stellar wind, and in this ocean things move. Pieces of one solar system are constantly being ejected, flung out by gravitational encounters, and sent on journeys lasting millions of years to wander through the territory of another. Our solar system is not an island. It is a port of call. It has a gravitational shoreline that is constantly being visited by flotsam and jetsam from distant unknown shores. You now live in a universe where the boundary of our solar system is not an end but a beginning. You live in a cosmos where the history of a star 100 light-years away can become a physical object in our own sky. It means that the galaxy is a far more interconnected, interactive and messy place than we ever imagined. The neat, tidy dioramas of planetary systems orbiting their stars in isolation are incomplete. We must now see them as part of a great galactic ecosystem, where material is exchanged, chemistry is shared, and the seeds of one world's formation can be sown in the cosmic dust of another. This realization carries with it a profound sense of both humility and connection. Humility because it underscores that our home is not unique or divinely separated. We are just one of countless collections of rock and ice, orbiting one of countless stars participating in a galaxy-wide exchange of material that has been happening for billions of years. But it also fosters a deep, almost spiritual connection. The atoms in your body were forged in the heart of a star that died long ago. We have always known we are made of stardust. Now we know that we are neighbours with other stardust, that the very fabric of our world is not isolated from the fabric of others. The journey of discovery sparked by Borisov is in the end a human one. It began with one amateur astronomer in his own small observatory driven by a passion for the night sky. His curiosity, magnified by the power of our global scientific community, reached across the chasm of interstellar space and pulled back a revelation. That revelation is that the universe is not something to be merely looked at. It is something we are fundamentally a part of a dynamic evolving tapestry in which our own solar system is just a single luminous thread. Look up at the night sky again. It is not the same sky it was before. Scattered among those familiar steadfast points of light are the invisible paths of countless other messengers, other pieces of other worlds sailing silently through the dark. They are on their way, carrying their own secrets, their own chemical stories. We may not see them yet, but we know they are coming, and now for the first time we know to look, we know to be ready. We are no longer just stargazers, we are watchers at the shore of the cosmic ocean, waiting for the next traveller to arrive.